this is lecture video 45, and we start chapter 8 in this video, which is the techniques of integration. And the first section of it, we will cover the integration technique called by integration by parts. Integration by parts is a technique to simplify integrals of this form, like integral of f of x times g of x dx, where f of x can be a polynomial, for example, and g of x is a trigonometric function, or f of x can be a polynomial of any kind, and g of x can be an exponential function, or f of x can be a polynomial, g of x can be a logarithm function. So here we are talking about products of two different types of functions, where the types are polynomials, trigonometric functions, or exponential function, or logarithm function. Or you may have like just the inverse trigonometric function, where you can think of f of x is just 1, g of x is arctangent x, or you may have just ln x, where again f of x is being 1 and g of x is ln x. Okay, so here what I try to emphasize is, if you have products of two different type of functions where the types come from polynomials, trigonometric functions, exponential functions, logarithm functions, also inverse trigonometric functions, you may think of integration by parts. Okay, here, what are the types? We will be using a very famous shortcut for the types of these functions. This shortcut is LAPTE, where L denotes the logarithm function, A denotes the inverse trigonometric functions like arctangent, arcsine, arccosine, any type can appear. P stands for the polynomials like x to the x square and all other different polynomials. Okay, T stands for the trigonometric functions. So what are trigonometric functions? Sine x, cosine x, tangent x, and there are a lot more. E stands for the exponential function, which is e to the power x, okay? So if you have products of any different two types of functions appearing in this shortcut, integration by parts technique may help you. How do we apply it? Here is the formula for it. Inside your integral, you will choose some part as u and some part as dv. Then this integral is written u times v minus integral v times u. I will show you how this is applied in the next example. But first, let me also put here the definite version of this formula. This is indefinite integral, you see, and the definite version, of course, will apply the same rule, v times du. The only difference is that you will be putting AB boundaries everywhere. Okay, like this. And this is the definite integral version of integration by parts formula. Okay, let's concentrate on the first example to understand how this formula is applied. This is the formula for integration by parts. Okay, look at our first example. We have a polynomial times a trigonometric function, right? So which one to choose as u and which one to choose as dv? The answer of this question is given by shortcut. Which function comes first in this shortcut? But whichever comes first will be chosen as u. This is the rule. So we have a polynomial and we have a trigonometric function, and you notice that p comes first in shortcut than the trigonometric function. That's why the polynomial part should be chosen as u. And the rest, the whole rest, will be chosen as your dv. Okay, now we are applying integration by parts formula. Okay, u is chosen as x, then dv is chosen as sine x dx. So you see, I covered this structure inside the integral. Now I need to compute what is du, what is v, because on the right hand side we will be writing them. So you will complete this diagram, okay? So if u is x, then du is dx. If dv is this thing, v is the integral of it. So from u to du, you pass by taking derivative, and from dv to v, you will pass by taking integral. Okay, what is integral of sine x dx? Obviously, it is minus cosine x. Then we will apply the formula u times v minus integral v times du. So it goes in this direction of the arrows. U times v, the minus integral sign we will put, then v times du. Okay, so maybe I should put here, you are integrating dv to find v. Okay, so the integral of sine x dx is just minus cosine x. So this integral in the question is evaluated as u times v minus integral v times du. So u times v minus integral v times du. This is the integration by parts formula given in the statement. Okay, we know everything. U is x. Okay, let's write down everything. V is minus cosine x, then minus integral v times du. So minus cosine x times dx. This should be computed here. So x times cosine x minus minus is a plus. Integral of cosine x is what? It is sine x. And since this is an indefinite integral, you shouldn't forget to put a general arbitrary constant c at the end. Okay, this is how you apply integration by parts. So look at this one, please. ln x dx. Let's write first our famous shortcut, labte. Which one comes first will serve as your u. So logarithm function comes first. That's why I will be choosing this part as u. Then the remaining part will serve as your dv. So it starts like this. U is chosen, dv is chosen. U is chosen as ln x, dv is dx. Then what is u and what is v? You need to complete this diagram. Here you will derivate, and from here to here you will integrate. Okay, what is the derivative of ln x function? It is 1 over x dx. dx is integrated as just x, right? Okay, and then you will be applying the formula in the direction of the arrows. So this integral goes like u times v, so x times ln x, minus integral this times this. So 1 over x times x is just, okay, v times du, right? Like this. This is v, this is du. I am doing what? I am doing u times v minus integral v times this part is just du. Okay, then after you simplify these two, you have x times ln x minus integral just x. Integral x is what? It is just minus x plus an arbitrary constant c. Okay, let's move on. Another example, x squared e to the power x. X squared is polynomial, e to the power x is exponential. We can be sure about which one is chosen to be u if you look at this shortcut. Which one comes first will serve as u, right? That's why we have p and e. P comes first, then e. That's why we understand that this is your u and this part will serve as your dv. Okay, u is chosen and dv is chosen. U is x squared, dv is e to the power x dx. Then from u, you can pass to du, and from v, we will find from dv to v, we will pass. Derivative is like that. Integral of e to the power x is itself, right? E to the power x. So use the direction of arrows to write down the result. It is x squared times e to the power x minus integral this times this. 2 comes out, x times e to the power x dx. Okay, now in this integral, you need to apply one more integration by parts because it is still in the form of a product of two functions. One of them is polynomial, the other one is exponential, two different types. That's why we will apply one more integration by parts. This is u, this is dv. Similarly to what we did above, u and dv is chosen. Okay, from u to du, from dv to v, we will compute. U is x, that's why du is dx. E to the power x dx, e to the power x. And then we multiply in the direction of the arrows. Okay, so what do you have for this integral? Let me write the overall result from the beginning on. So it is x squared e to the power x 2 times x times e to the power x minus integral e to the power x dx. Okay, so the result is e to the power x minus 2x e to the power x minus. The result of this integral is e to the power x, and don't forget to put your arbitrary constant c at the end. Okay, let's move on. What type of functions we have here? This is the exponential function. And this is the trigonometric function. Write down your shortcut. Which one comes first will serve as your u. Trigonometric comes first, then the exponential function. That's why we will choose trigonometric part as u function, and the rest will serve as dv. Okay, so like this. So u is, we are applying integration by parts here. So u is chosen as the trigonometric function, and dv is chosen as the exponential function. Okay, this is sine x, and this is chosen as e to the power x dx. Derivative of sine x is cosine x dx. Integral is e to the power x, and then we will apply integration by parts formula. So the integral of this thing is, okay, let's write down what we have after applying integration by parts is this times this, sine x times e to the power x minus integral e to the power x times cosine x dx. You see, we need to apply one more integration by parts here. So Lapte, exponential, trigonometric, and just like we have here, trigonometric comes first, then exponential. That's why we will choose trigonometric function as the u, and the rest will be chosen as dv. Okay, construct your diagram again. U and dv is chosen, then we will compute these two things. U is cosine x, du is derivative of cosine x is minus sine x dx. dv is this part, and integral of it is just e to the power x, and then follow the direction of the arrows to apply the integration by parts formula. So what you have? You have sine x e to the power x is this term minus this times this, right? Cosine x times e to the power x minus integral this times this. There's another minus here. That's why e to the power x sine x dx. Okay, this is what we have. And remember, we were trying to compute this integral. And you see, the question that we are trying to solve appeared again in the solution. This type of situations happens sometime. Your original problem appears in your solution, but this was what we are trying to solve, and it is appeared again. So we will solve this equation in terms of this integral. So let's take it to the right-hand side. Okay, or you can call it as I. You are trying to solve this integral. So what do you have this in this equation? I equals sine x e to the power x cosine x e to the power x minus another I. And you want to solve for I, that's why you can just take all the i's to the left side. Okay, so let me write it in this parenthesis form. E to the power x sine x cosine x. From here, the original problem, which you denote as I, is solved as this expression divided by 2. Okay, so sometimes while applying integration by parts, the original question may appear in your solution, but that's not something bad because you can just take every I to the left-hand side and solve for it. Okay, let's solve one more example. Here we have a definite integral. By the way, I just forgot to put here an arbitrary constant c because the integral was an indefinite one without any boundaries. Okay, for this one here, we have a definite integral. So let's choose this part as u and this part as dv, shall we? So u du, we choose dv, and then I will write what is v. Okay, u is x, du is dx then. This is what we have for dv, and the integral of this expression is what? Okay, let's try to handle it separately here. We want to integrate this, and you can use substitutions. If this is u, then this is minus du. That's why the integral is square root of u du, so minus u to the power this. So it is just a power function. So you will add 1 to the power, divide by the same power like this, where u is 1 minus x. Okay, so the result here, v is the integral of this square root expression, which is this one. So it is 2 over 3, 1 minus x, like that. And then now I will be following the directions of these two arrows to apply integration by parts. So it goes like x times this expression. So x times minus 2 over 3, 1 minus x, 3 over 2. So this time it is a definite integral. That's why I will evaluate this first part from 0 to 1 minus integral. So you see, this times this. So another, okay, I will just, so minus integral, this expression times this. Since this is also minus, it will become a plus. This goes out like that, dx. The boundaries of the integral is obviously from 0 to 1. Okay, then let's evaluate this integral. So you can just call this part as u, and this part will become minus du. That's why the result is, okay, let me write out, 1 minus x from 0 to 1. So plus, okay, plus 2 over 3. This is evaluated as you add 1 to the power, divide by the same power. There is another minus sign here. That's why I will change this plus to a minus. So add 1 to the power, divide by the same power. You have your expression here, and then you will evaluate this integral from 0 to 1. If you insert all the boundaries to your expressions, you will find the result as 4 over 15, okay? So in the definite integral case, while applying integration by parts, you still complete this diagram, and then you follow the directions of arrows. The only difference is that you are evaluating from 0 to 1, 0 to 1. Okay, and finally, I want to show you this example, which we call as the tabular integration. So this is a quick way of applying integration by parts over and over again. You see, this is a very high power, meaning that you will apply 4 times integration by parts to get rid of this polynomial part. So you can just write u dv's every time you apply integration by parts, but there is another quick way of finding the result here, which is called tabular integration. So it works like you put x to the power 5, this is the part for u, and the rest is your dv, right? And every time you apply integration by parts, you will be taking the derivative, right? So you will take the derivative consequently of this expression. You will take the integral of this thing over and over again. So it is 5x to the power 4, 20x cubed, 60x squared, 100 and this, and 0, till it disappears. You take the derivative like this, and here at every step you will be taking the integral, e to the power x, e to the power x, and we are lucky the integration of e to the power x is always itself. Then you start multiplying, and you start following the directions of arrows. If you remember, it was like this. So this with this, and this. So you put plus, minus, plus, minus, plus, minus. This is also the part of the rule. You start with plus and you always change the sign at every step. So the result is written by looking at this table. So it is plus x to the power 5, e to the power x, then minus 5x to the power 4, e to the power x, then plus again 20x cubed, e to the power x, minus, plus, and minus. Did I write everything? So, okay, let me see. Minus, yeah, I am here. 6x squared e to the power x, and I continue from here, 120x e to the power x, then minus, this will be the last term in your result, e to the power x. Since this is an indefinite integral, you will put this extra constant c there, okay? I think I will also solve this example and then stop. What we are doing here is applying integration by parts, I think 6 or 7 for 6 times. And the quick way of applying integration by parts formula is doing like this: derivates at every step, this part integrates every step and write like this. This is called tabular integration. Okay, final question. We have a polynomial, we have a trigonometric function, lapte, which comes first will serve as our u. So which one is first in our shortcut? Polynomial is before than the trigonometric. That's why this part is your u and this part is v, dv. So we choose u, we choose dv. From u to du, dv to v, we will write x, derivative of x is just dx. dv is secant square x dx, and the integral of secant square is tangent x, remember? Okay, then we will follow the direction of the arrows to find the result of this integral by applying integration by parts. Here we are applying integration by parts. Okay, so follow the arrows. X times tangent x minus integral tangent x times dx. Okay, then what is this integral? You can easily compute it by writing, by writing tangent x in the form of sine x over cosine x dx. So if you choose cosine x as your u, so let's try to apply a substitution here. And sine x dx is minus du, because derivative of cosine is just minus sine. Okay, let me write down. We choose u as cosine x, du is minus sine x dx. That's why sine x dx is in fact minus du. So what you have here is minus minus plus integral of du over u, right? So by using this substitution, your integral looks like this, and it is in fact evaluated as ln absolute sine of u. So minus minus plus du over u is evaluated as absolute sine of u. And then at the end, you will put this extra arbitrary constant. Okay, so I stop here. The remaining for 1, 2, 3, 4 questions will be exercise for you. Thank you for your attention.